This is a question from AQA A-level Chemistry. It's from paper 3 and this is part of the required practical assessment playlist. We're focusing on RPA3 here and this is the second question in the series. Going to recommend as always that you pause on the screen where the questions are present, have a go at them and then watch the rest of the video to review your answers. So here are parts A, B, C and D. And here we've got parts E, F, G and H. So let's take a look. Going back to part A, we've got here the idea that hydrogen peroxide and iodide ions are reacted in acidic conditions. We can see it's acidic conditions because there are H plus ions present on the left hand side of the equation. And we've been given the rate equation here, which includes H2O2, I minus and H plus. In an experiment to determine the order with respect to H+, a reaction mixture is made containing H+ ions with a concentration of 0.5 mol dm to the minus 3. And a large excess of H2O2 and I- are used, so the rate equation is simplified to just include H+. Explain why the use of a large excess of H2O2 and I- means the rate of reaction at a fixed temperature depends only on the concentration of H+. Well, actually, if we have a very large excess, it means that any small changes have minimal effect. So we're essentially saying that their concentrations are kept effectively constant. And if they're constant, we don't need to include them in the rate equation. We can say that they are zero order with respect to them. Moving on to part B, samples of the reaction mixture are removed at timed intervals and titrated with an alkali to determine the concentration of H+. What must be done to each sample before it is titrated with alkali? So you need to go through a couple of steps here. You do need to stop the reaction. You need to make sure that it is not continuing to react before you do the titration. And the way that you can do that is to dilute or to cool that solution. That will effectively stop it, and it means your titration you're going to get valid results from. Okay, how does this graph show that the order with respect to H+ is 0? Well, what we're looking for here is that we are seeing a constant gradient as the concentration of H+ changes. Finally, going on to part D on this section, use the graphs in figure 1 to calculate the value of K1 and give the units. So I've put these lines in so we can see. I'm going to work out the gradient of the line and I'm using as much of the space as possible. So I can see here that I've got 415 on the x-axis and 0.5 on the y-axis. So my gradient is going to be 0.5 over 415, taking me to a value of 0.0012. For my units, I've got mol dm to the minus 3 per second, which is the standard unit for rate of reaction as well. Okay, we're going to move on. We're going to look at E, F, G and H. So part E, second reaction mixture made at the same temperature. Initial concentrations of H+ and I- are both 0.5. There is a large excess of H2O2. In this reaction mixture, the rate depends only on the concentration of I- and the results are provided in the table. So your first point is to plot the remaining parts on the graph. Easy marks, but only if you take the care to do them diligently, to do them accurately. So I'm putting those points in. And actually what really stands out here is I've got quite a clear pattern if I remove my anomaly. So when I draw my line of best fit, I'm not going to include the point at 400, but I have got a pretty smooth curve for the remainder. Now from there, we're going to move on because we want to calculate the rate of reaction when H+ is 0.35. Now this is not asking for the overall rate of reaction, it's asking for the rate at a specific point in time. And this is where you need to recognize that you've got to use a tangent to the line, which I've added at 0.35. Remember, a tangent must only touch the line at that one point. It must not cross it. I can now do my gradient calculation. I've got here 1200 and I've got 0.46. change in y over change in x, 0.46 over 1200, and I get my rate calculated as 0.000383 or 3.83 by 10 to the minus 4, and we have got our final answer and 2 marks. The final part here is a 6 marker and follows normal 6 marker patterns. I'm going to change the structure here just so you can see where you're going to get a level 3, a level 2 or a level 1. Commonly, there will be 3 specific areas that you're looking to gain marks in, and it explains on the right, if all stages are covered and virtually complete, you're going to get level 3, 5 or 6 marks. If all stages are covered but not virtually complete, you can get to level 2, or if 2 stages are virtually complete, it's level 2. Level 1 is if you've attempted 2 stages or have virtually completed 1 stage. Anything less than that is level 0. So what's key here is finding out what the 3 stages are. Stage 1 is the preparation. Let's look at the question actually. A general equation for a reaction is shown. A plus B plus C goes to D plus E. A, B, C and D are colourless, but E is dark blue. A reagent X is available that reacts rapidly with E. This means that if a small amount of X is included in the initial reaction mixture, it will react with any E produced until all of the X has been used up. Explain, giving brief experimental details, how you could use a series of experiments to determine the order of this reaction with respect to A. In each experiment, you should obtain a measure of the initial rate of reaction. Remember, initial rate of reaction, you draw a tangent to the line at 0 seconds. But stage 1, the preparation. You're going to measure stated volumes of named reagents. You can specify what that volume is, but you can say stated volumes. You're going to measure a known amount of X in separate containers. You are then going to add X last. So you do the reaction, you add X. Stage 2 is for the procedure. So to be virtually complete, you would probably need to get 2 of those 3 in stage 1 to be credited as virtually complete. Stage 2, the procedure. You're going to start the timer at the point of mixing. All mixed, give the mark even if X isn't added last, so you're not losing marks for compounding an error. You're going to take the time recorded for a cross to disappear. Remember, we're being told here that we're producing something that's dark blue. So we're looking at how long it takes to not see the cross. You're going to keep the concentrations of B and C equal because we want to know the order with respect to A. We're going to try and keep the temperature the same, so we can use a water bath, so we can keep that control variable. And then you're going to repeat that experiment, but with different concentrations of A. So that's stage 2 procedure. There are 5 of those. You probably need to get 4 of those 5 to be considered virtually complete. And then we move to stage 3, the use of the results. 1 over time taken is used as our measure of rate, so 1 over T, really quite familiar in these sorts of questions. You're going to plot 1 against T against log of concentration of A. Again, this will be familiar from the required practical that you've carried out. And then you're going to describe how you're going to use the graph shape to interpret the order. So that takes you back to the theory about whether that's a straight line graph, a curve, etc. And you can go back to your notes and find that information. So that takes us to the end of this question. Thank you for listening and goodbye.